saying, right, the mass flow rate over here, what is the definition of mass flow rate? Rho A B. For this kind of compressible flow, phi will be Mach number C, which is equal to Mach number ART. Now you put it there. Rho A Mach number ART. Now what rho? P over RT. So we change that. Rho is equal to P over RT. So we add here P over RT. Okay? Now you know the definition of T as a function of T naught. What's that?
Where's my right now?
T naught is equal to T plus P squared over 2Cp. And this P is this one. So you put this into here and you put this in terms of T into that. Okay, get that. Then you trust that one. Right? The rule is still the same. If you don't trust this one, derive on your own. Okay, and I hope you don't trust this one. So you hope you will derive on your own. And then P, similarly, when you have P naught, T naught over T A minus 1, right? So you put this one, put here, by mathematical formulation, you get this thing, if you believe me. If you don't, you can derive it on your own. Better? Any question till now? So, using this, you have this mass flow rate that flow through the nozzle. Okay? And you know that the maximum Mach number can be achieved by converging nozzle is 1, right? Okay. So the maximum Mach number can be achieved by this kind of nozzle is 1. So if you introduce that, you put this one equal to 1 and this one equal to 1, right? You get this, okay, which is the maximum mass flow rate through a nozzle. So what's the condition you can reach this maximum flow rate? When you reach the critical condition. Right? So it will only happen in the throat when the Mach number is unity of 1. Okay? This condition, okay, this condition gives the application of nozzle for flow meter in a compressible flow. In fluid mechanics 1, you see something like this. And it's also used for a flow meter. What's the name of that thing? Venturi meter. In your opinion, is it the same with this one? The Venturi meter that you learned in fluid mechanics 1, is it the same concept with the flow meter using this nozzle? Huh? Converging, diverging for the Venturi meter. Okay. Yes, of course. The fluid is different. For the Venturi meter, we are using the Bernoulli concept, where it is derived only for a incompressible flow, where your density is not there. In this case, it is used for compressible flow. You know why it can be done is because you know that at the throat, when you have critical condition in here, the Mach number will be 1 and the flow rate will be maximum. Okay? So if you look at the maximum flow rate, if you want to control the flow rate, what will you do? You want to use the nozzle to control the flow rate of compressible gas. So what will you control? Area, pressure, which pressure? P naught. And then the temperature. Okay, very good. So this condition gives you the flexibility to use the nozzle as a flow rate controller. Okay, so it's very important in the chemical process and medical devices where the mass flow rate is important. Now, if we look back at this, you can see this one is the condition where PB is equal to P naught. P naught is condition over here. When the pressure over here is equal to pressure over there, there will be no flow rate, or the flow rate will be 0 when PB is equal to P naught. When you reduce the PB into half or in the point 2, actually point 2 is along this point, any point, as long as PB has not reached the P star, so you will see that the mass flow rate will increase until it reaches the maximum flow rate. When it reaches the maximum flow rate, right, when it reaches the critical condition, further increase or further decrease in PB will not give any changes to the flow rate. You have reached the maximum flow rate. That's why this kind of flow is called. So if you do like Superman, you will get. Okay, fortunately we are not Superman, so we will never reach the critical condition. Okay, so we look at this one, the exit plane pressure. What's the difference between exit plane and back pressure is this. The PB is in the reservoir, but the exit pressure is exactly at the exit plane. Remember, exit plane, not the back pressure, the exit plane, exactly at the exit surface of the nozzle. Okay, so the exit pressure will be equal to the back pressure when it is more than P star or equal. But when it's less than that, actually the exit pressure will be equal to P star. So it doesn't really matter whether you make it vacuum, right? You make it vacuum. Once it reaches the P star, it will never goes down. It will stay at the P star. That is the minimum pressure you can achieve using this converging nozzle. Any question? Okay, so easy to understand. Okay, so you see here when PB is equal to P naught, you know that exit will be equal to PB. Right? P naught, P naught. So PE equal to PB, right? When PB is equal to P star, then the exit will be equal to P star. When PB is less than P star, the exit will be equal to P star. This is how to read this graph. Okay? And also, based on our mass flow rate formula, you can see that if you want to increase the maximum flow rate, you can either increase pressure or decrease the temperature or increase the area. Okay? So if you want to increase the mass flow rate, you can decrease PO or increase PO or decrease, if you want to make it lower, you decrease PO and increase PO. Okay? And if you see here, when P exit is equal to the inlet, there will be no flow. As you reduce it further, it will increase until you reach the maximum condition. Okay? And then, this one, if you look at this and this, you know that in this case is only achieved when Mach number is equal to 1. And it will only occur at the throat. So you always know that the area is the area of the throat. Okay? This can occur in any location. Right? In any location. So this Mach number can be any value, and this area can be any value. If you take a ratio between this and that, you will get this. Equation is the one that we need to solve our tutorial question 3. So some of you who have the tutorial tomorrow, you are in a little bit advanced. We will move to question 3. Right? Yesterday tutorial stopped at question 2 only. Okay, but we finished earlier. Right? So if you take the ratio of A for particular Mach number to the area of the throat is given by this. Right? So let's say you want to calculate the area where the Mach number is 0.8 when the throat area is 20 cm squared. You can do that. Right? You put this one 0.8, 20 cm squared. So then you get your A star. Any questions so far? No. Okay, easy? Now if you think it is easy, we have a problem example later on. Okay, another parameter sometimes is used in the analysis is called Mach number star. Or this Mach number is the velocity with respect to the C and the throat. Can I erase this one?